Hello everyone, thank you very much for signing in and watching my live stream. I'm Mr. Matt and this is Dr. Tot. Dr. Tot, do you want a cookie to start class? Very good. And welcome to SAT, ACT Prep. So today we're going to go through some miscellaneous practice problems. We're going to approach these problems in pairs and then do clusters of 3 so you get ample exposure to each type of subtopic that's being tested. So let me go ahead and share my screen with you. If you have any questions, then please let me know. If you find these videos helpful, then please hit that like button. And just a friendly reminder that these are live sessions, so there is a little bit of a delay with the iPad, but I'm going to mitigate that as much as possible by monitoring the live screen. So this document, after it's posted, will be available on Certified Learning Center's website, but you can follow along also just by looking at the screen. So let's look at questions 1 and 2. So question number 1 asks, what is the area of an equilateral triangle with a side length of 10? And number 2 asks, if the diagonal of one of the 6 faces of a cube is 4 root 2, then what is the volume of the cube? So I'm going to give you 6 minutes, and I'll keep track of the time in the upper right-hand corner, and I'll update the time per minute. And then 2 minutes into that, I'll start to solve. So if you get stuck and if you need some hints, you can just look at the screen before the 6 minutes expires. Okay, so 6 minutes, and then we'll review completely. Okay, so if we look at number 1, so they give us the side length of the equilateral triangle to be 10. All equilateral triangles have equal sides and they are equilateral and equal angular, meaning that all of the angles have to be the same measure. If the total sum of the degrees, the interior angles of a triangle has to be 180, and all 3 of the angles have to be the same measure, then 180 divided by 3 is 60, meaning that in every single equilateral triangle, all angles are 60 degrees. So if you were to bisect that equilateral triangle, or if you bisect any equilateral triangle by its altitude, by its height, and that's the distance directly from the vertex down at a perpendicular at 90 degrees with the base. So from the vertex to the base at a 90-degree angle, that is the height or the altitude of the triangle. If you bisect an equilateral triangle by its altitude, that's going to produce 2 30, 60, 90 special right triangles. Now we're going to have a whole section on these special right triangles, but this is just a snippet of what we're going to get into. The power of these ratios, these angle to side ratios, is that they go further in concept than the Pythagorean theorem can, because you can solve for all sides of a triangle knowing just one of the given sides, or just being given one side, versus with the Pythagorean theorem you need at least 2 sides to solve, because it has 3 variables in the Pythagorean theorem. Here, if we know that the side length of the triangle is 10, that means that the hypotenuse of the smaller triangles, if we just look at one of the sections that I'm going to highlight here with the red highlighter, one of those bisected 30, 60, 90 triangles, the side length of 10, what used to be the side length of the equilateral triangle, would now be the hypotenuse of that 30, 60, 90 triangle. And so every single 30, 60, 90 triangle has side ratios that correspond to those 30, 60, 90 angles in a ratio of 1 to root 3 to 2. So if you write your ratio, that's how you start, just 30, 60, 90, which corresponds to side lengths in a ratio of 1 to root 3 to 2, and then draw a line underneath of that given ratio. Now you need to place underneath of that standard ratio. That's what you're always going to write. But now you need to place the given value in the problem with the correct corresponding angle measure and side length ratio element. So we were given 10. 10 is opposite the 90-degree angle measure of that 30, 60, 90 triangle. So I put it underneath of the ratio element 2 that corresponds to the 90-degree angle. Then I asked myself, to go from 2 to 10, what is the common multiple? That's 5. Only 2 times 5 will give me 10. So I need to multiply the other ratio elements, root 3 and 1, by 5 in order to get the other 2 missing side lengths of that 30, 60, 90 triangle. That's important because the side length that is opposite the 60-degree angle measure in those smaller triangles is the same thing as the height of the equilateral triangle. And the area of any triangle, the formula for the area of a triangle is 1/2 base times height. So we need to use this in order to find the height of this triangle, because we know the side length, but that's not the same thing as the height. So multiplying by 5, I'm going to find that the side length that's opposite the 60-degree angle measure is going to be 5 root 3. So that is the height of the triangle. Now I have the base, which I know all sides of the equilateral triangle are 10. So if one side is 10, all of them have to be 10. So the base is 10 and the height is 5 root 3, so I can plug that into the area formula of 1/2 base times height. So I'm going to get 1/2 times 10 times 5 root 3. 1/2 times 10 is 5. 5 times 5 root 3 is going to be 25 root 3. There's no radical attached to that first 5 to affect the radicand of 3 in the second number. So that 5 is only going to affect the leading coefficient of that radical, which is another 5, and 5 times 5 is 25. So our answer here is going to be 25 root 3. There is a shortcut only for equilateral triangles. So if you memorize this formula, which is never going to be given, but equilateral triangles do come up often, often enough for this to be significant, and it's a real time saver. So the area of any equilateral triangle is equal to its side length squared times the square root of 3 quantity divided by 4. So if you are able to remember that, if we plugged in the side length of 10, we would get 10 squared, which is 100. So the numerator would be 100 root 3 quantity divided by 4. Well, 100 divided by 4 is 25. So the answer, we would get the same answer of 25 root 3. So the answer to number 1 is C, 25 root 3. For number 2, they ask if the diagonal of one of the 6 faces of a cube is 4 root 2, then what is the volume of the cube? So now the face of a cube is going to be a square. If you divide a square by its diagonal, that will always, not a rectangle, but a square, because remember, a square is a special type of rectangle where all sides are equal. But if you divide a square by any one of its diagonals, that will always produce two 45, 45, 90 degree triangles. And just like 30, 60, 90 triangles, these have very specific angle to side ratios, and they're always constant. So just knowing one side length, we're able to solve for the other two missing side lengths. That ratio is when the angles are in a ratio of 45 to 45 to 90, the side lengths are in a ratio of 1 to 1 to root 2. So again, just start by, once you identify that you're working with a 45, 45, 90, just start by writing out that ratio, 45 to 45 to 90. Underneath of it, write in the side length ratios of 1 to 1 to root 2. Then draw a line and correspond the given side length of 4 root 2, which is the diagonal of that square. What is that diagonal in the perspective of the triangle, of the 45, 45 triangle? It's the hypotenuse. It's the side length opposite the 90 degree angle measure. So underneath the ratio element that corresponds to 90 degrees, I'm going to write the given value of 4 root 2. Now, in order to go from the ratio element of root 2 to 4 root 2, what do you need to multiply by? What number times root 2 is 4 root 2? Well, you just multiply by 4. So I'm going to multiply the other ratio elements of 1 by 4, and you can see that the side length of this cube, well, specifically the side length of this face of the cube, which means all side lengths are equal, so the side length of the cube overall has to be equal to 4. The volume of a cube is equal to side length cubed. So substituting 4 into that volume equation of side length cubed, I'm going to get volume is equal to 4 cubed, which is 4 times 4 times 4, which is 64. If you have any questions, then please let me know. Otherwise, let's look at 3 and 4. Number 3 asks, what is the area of an equilateral triangle with an altitude of 6 root 3? Number 4 asks, what is the diagonal of one of the 6 faces, if the diagonal of one of the 6 faces of a cube is 6, then what is the volume of the cube? So again, I'll give you 6 minutes and update the time per minute. After 2 minutes, I'll start to solve to give you some hints. Okay, so for number 3, if we know that the altitude is 6 root 3, then we can plug it into, or we can use the fact that when we divide an equilateral triangle in half, it's going to turn into two 30, 60, 90 triangles. And that altitude is the height of the equilateral triangle, but it's also the long leg of the 30, 60, 90 triangle. So we can use that to solve for the side length. Once we know the side length, that's going to be all the sides are equal in an equilateral triangle. So we get one side length, we'll know what the base is. Then we'll have the base and the height, which is what we need to solve for the area of the overall triangle. So if we know that it's a 30, 60, 90 triangle, or it splits into two when we bisect it by the height, the given value is across from the 60-degree angle measure. So I put that in orange underneath the root 3 ratio element. To go from root 3 to 6 root 3, we need to multiply by 6. So I'm going to multiply the other ratio elements of 1 and 2 by the common multiple of 6. And so this right here would be, actually let me do it in the same color. So this little segment, which is half of the base, would be 6, and this hypotenuse is 12. And that makes sense because the altitude is splitting the equilateral triangle into two congruent 30, 60, 90 triangles. And so if the overall hypotenuse is 12, it makes sense that the two other long legs of the two triangles are each 6. If you add them together, you get 12. So the base here is 12. The height is 6 root 3. So the area is going to be 1/2 times the base, which is 12, times the height, which is 6 root 3. 1/2 times 12 is 6. 6 times 6 root 3 is 36 root 3. That's answer selection D. Notice that once we have the side length, we could have also used the area equation that's specifically for equilateral triangles. That's s squared times the square root of 3, quantity divided by 4. So if we knew that the side length was 12, this would be 12 squared times root 3 over 4. 12 squared is 144, so we get 144 root 3 over 4. 144 divided by 4 is 36. So we do actually get the same answer of 36 root 3 with the shortcut as well. For number 4, so here we had, this problem was a little bit more difficult because we're going from a radical to an integer value. So we need to break this up into 2 steps in order to figure this out. So if they tell me that the diagonal of one of the faces of the cube is 6, I know that each face of the cube has to be a square, and the diagonal of a square will divide the square into two 45, 45, 90-degree triangles, which have very specific angle to side length proportionality. So if I use the 45, 45, 90 ratio of 1 to 1 to root 2, I just set that ratio up by writing it out vertically. And then I draw a line. I position the given side length of 6 underneath the ratio element that corresponds to the 90-degree angle measure, because the side length of 6 is across from the 90-degree angle measure in that 45, 45, 90-degree triangle. But the problem is that I need to go from a radical of root 2 to an integer value, a whole number of 6. So you break this into 2 steps. First, get rid of the radical. And you do that. I did this in the bottom left-hand corner in orange and green. And I'll highlight this here in blue. I'm going to draw a blue square around it. So first, to go from root 2 to 6, first get rid of the root 2. So if you multiply root 2 by itself, whatever it is, whatever the radical is, if you multiply it by itself, that's going to eliminate the radical, because root 2 times root 2 is the same thing as root 2 squared, which is 2. Now you can ask yourself, okay, to go from 2 to 6, what do I need to multiply by? Now you know it's pretty easy because you're going from an integer to another integer. To go from 2 to 6, you need to multiply by 3. So you put the two factors together. First you multiplied by a multiple of root 2, then you multiplied by a multiple of 3. 3 times root 2 is going to be a comprehensive common multiple of 3 root 2. So you just need to break it up into multiple steps to make sure that you don't make a mistake, or that to make it easier. So 1 times the ratio elements corresponding to the 45 degree angles are just ones. So 1 times 3 root 2 is just going to be 3 root 2. So the side lengths of this face of the cube, and therefore the side length of the cube overall, because all side lengths in a cube are equal, is 3 root 2. The volume of a cube is side length cubed, so we're going to have 3 root 2 cubed. Now just apply that exponent of 3 to both the coefficient and the radical. Now root 2 to the third power, that's root 2 times root 2 times root 2. So that does end up becoming 2 root 2, because root 2 times root 2, as we've seen before, eliminates and becomes root 2 squared, which is just 2. So 2 of the root 2's eliminate to a regular 2, but you're still stuck with 1 of the root 2, so it becomes 2 root 2. So we're going to have 3 cubed times root 2 cubed, which turns into 3 cubed is 27, root 2 cubed is 2 root 2, and so 27 times 2 is 54, so our answer here is going to be 54 root 2, which is answer selection A. If you have any questions, then please let me know. Otherwise, let's look at 5 and 6. Number 5 asks, what is the area of an equilateral triangle with an altitude of 12? 6 asks, if the diagonal of one of the 6 faces of a cube is 5, then what is the volume of the cube? So I'll give you 6 minutes. I'll update the time per minute, and then and then I'll start to solve after 2 minutes. Okay, so for number 1, they tell us that the altitude is 12. So we can split that equilateral triangle by its altitude and produce two 30, 60, 90 right triangles. We know, therefore, that the side length that's opposite the 60-degree angle measure is the same thing as the altitude of the equilateral triangle, and both of those, they tell us, is 12. So going from the ratio element of root 3 to the given side length, or the given altitude length of 12, we need to go from the radical root 3 to 12, so I'm going to multiply by root 3 first. Root 3 times root 3 will give us 3. Then to go from 3 to 12, you multiply by 4. So putting together the root 3 and the 4 multiples, 4 times root 3 is 4 root 3. So the common multiple that we need here to transform the given ratio elements to the actual triangle side lengths is 4 root 3. 1 times 4 root 3 is 4 root 3. 2 times 4 root 3 is 8 root 3. So the side length of the equilateral triangle overall, which would be the same thing as the side length opposite the 90-degree triangle, the 90-degree angle in the 30, 60, 90 triangle, is 8 root 3. So if we plug that into the area of an equilateral triangle is equal to side length squared times the square root of 3 quantity divided by 4, then we're going to get, 8 root 3 quantity squared times the square root of 3 quantity divided by 4. So apply the square separately to the 8 and then to the root 3. So 8 squared is 64. Root 3 squared will just turn into 3 because it cancels with the radical. And then I eliminated 4 into 64 because 64 divided by 4 is 16. 16 times 3 is 48. So that'll give us 48 root 3. For number 6, if the diagonal is 5, then we know that the diagonal of a square will split the square into two 45, 45, 90-degree triangles. So using that ratio, this one's a little bit trickier. They throw in an extra step. So to go from root 2 to 5, first we need to get rid of the radical. So I multiplied root 2 times root 2, and that got me 2. But 5 is not a direct multiple of 2. So what you need to do is you multiply by some fraction that has the numerator of what you want and has a denominator of what you want to get rid of. So right now, after I multiplied by root 2, I have 2. But I need to go from 2 to 5. So I'm going to put 5 in the numerator, and I'm going to put 2 in the denominator. So then when I multiply by 2, or when I multiply 2 by this common multiple of 5 over 2, that's going to eliminate the 2 in the denominator and replace it with the 5 in the numerator. So that will end up being 5. So putting these two common multiples together, 5 over 2 times root 2, which remember root 2 you can think of as root 2 over 1, that's going to turn into 5 root 2 over 2. So the common multiple here is 5 root 2 over 2, which multiplying by the common ratio elements of 1 that correspond to the 45-degree angle is just going to give us side lengths of 5 root 2 over 2. So the volume of the cube is side length cubed. So we're going to have to cube that expression 5 root 2 over 2. You just apply that cube to each value, apply it to the 5, apply it to the root 2, and apply it to the 2. 5 cubed is 125. Root 2 cubed is root 2 times root 2 times root 2. So one pair, 2 of the root 2's will cancel, the radicals will cancel and turn into a regular 2. But that leaves one of the root 2's behind. So root 2 cubed turns into 2 root 2. And 2 cubed is 8. So we get 125 times 2 root 2 over 8, and that coefficient of 2 will eliminate with one of the factors of 2 and 8, and so our final answer here is going to be 125 root 2 over 4. That's answer selection C. If you have any questions, then please let me know. Otherwise, let's take a look at another pair of questions. Number 7 asks, for how many positive integers of x does the function f of x is equal to, this is a rational function with the numerator of the square root of 4x minus 8 and a denominator of x squared plus 2x minus 3 have no real values. So for how many positive integers of x does that function have no real values? 8 says how many points of intersection are there of the functions g of x is equal to 2 times the quantity x minus 2 quantity squared, quantity plus 3, and j of x is equal to 1/3 times the quantity x minus 2 quantity squared, quantity plus 2. I'll give you 6 minutes, and after 2 minutes I'll start to solve. Okay, so when answering number 7, you really have to focus in on the phrase that has no real values. So if the function has no real values, that means that the function doesn't exist at a particular input. That's only going to occur, one, if the function has some type of discontinuity, some type of hole, some type of asymptote, and that occurs because there's a violation of a mathematical principle involved. That usually doesn't occur. This is kind of a rare circumstance. However, there are a few things in math that you're not allowed to do. So for example, it doesn't make sense to take the square root of a negative value without factoring out an I, and we'll learn about I later. That's how mathematicians do take the square root of negative values, use I. But anyways, you're not allowed to take a square root of a negative number, and you're also not allowed to divide by 0. So any input of x that would make the radicand in that numerator, underneath that radical sign, that expression 4x minus 8, any input value of x that makes that negative would necessarily mean that the function overall is violating a mathematical principle of dividing, or of square rooting a negative number, and therefore doesn't have an output at that particular input. So I'm going to take that expression of 4x minus 8 and set it equal, or set an inequality, write an inequality, and make it less than 0. Because any value that results in an output less than 0 would result in a negative output, because all negative numbers are less than 0. So when I said 4x minus 8 less than 0, now solving for x, I would add 8 to both sides and then divide by 4. So I get x is less than 2. Notice that doesn't say x less than or equal to 2. That says x less than 2. There's only one positive integer less than 2, and that's x equal to positive 1. So I have one positive integer so far for x that would not, or that would produce non-real values. So now let's look at the denominator, that polynomial or trinomial of x squared plus 2x minus 3. We can factor that into x minus 3 times x plus 1, and then use the principle of zero products. Remember that anytime you have products, or two values, two things multiplying times each other, and they equal 0, you can set each of them equal to 0 and solve. So if we know that the quantity x minus 3 times the quantity x plus 1 is equal to 0, then we know that x minus 3 has to be equal to 0, and x plus 1 has to be equal to 0. Adding 3 to solve for x in the first equation, we'd find x to be equal to positive 3. Subtracting 1 in the second equation to solve for x, we'd find x is equal to negative 1. But negative 1 is not positive, so we don't count it. So in total, there's positive 1 and positive 3, which is a total of 2 positive x values that would produce non-real outputs. So the answer to number 7 was C, which is 2. For number 8, how many points of intersection are there of the functions g of x is equal to 2 times the quantity x minus 2 quantity squared plus 3, and j of x is equal to 1/3 times the quantity x minus 2 quantity squared plus 2. So remember that these two guys are in vertex form. The outside coefficient, so the leading number outside of the parentheses, is your stretch or shrink factor. That's going to make the graph either wide or really narrow. It's either meaning that it's increasing slowly when it's wide, or it's increasing very rapidly when it's narrow. Also, when that leading coefficient is negative, that means it's flipped around the x-axis. So that means it's going to be facing downward when the a value is negative. The h value, the value that's inside of the parentheses next to the input variable of x, is your horizontal shift factor. Notice that that implicitly has a negative sign next to it in the formula. That means that the h value is opposite common sense. It's going to appear the opposite of how it actually is. So when we see, for example, in the given equations, x minus 2, for a horizontal value of minus 2, you would normally think that that means left 2. that is opposite common sense, it actually is right to. So we're going to go right to, and then the k value goes with common sense. That's the vertical shift. So in g of x, we have a horizontal shift right 2 and up 3. That describes the position of the vertex. So if I plot that point, and then I can understand that relative to the second equation, the first stretch factor is rather large. It's greater than 1. So the a value in the first equation is 2. The a value in the second equation is 1/3. When a is greater than 1, that's going to produce a very narrow graph because it's going to increase very fast. When a is in between 0 and 1, that's going to produce a very wide graph, or relatively wide graph, because it's going to increase slower. When a is negative, that means all the same proportionalities are going to still apply. So if it's in between 0 and 1, it's going to be relatively wide. If it's if it's in between 0 and -1, it's going to be relatively wide. If it's less than -1, it's going to be relatively narrow, but they're going to be all flipped around the x-axis facing downward because the leading coefficient is negative. So when the a value is negative, you still have to think about whether it's in between 0 and -1 or whether it's less than -1. But overall, it will be downward facing. Here, the second equation has a value in between 0 and 1, so it's going to be relatively wider. And it has a vertex of 2, 2, because we have a shift right 2 and up 2. So I plotted that point. And then I just sketched graphs, not anything exact, but I know that the first one is narrow and the second one is wide. So you can see that because the second graph is set below the first graph, and it increases very slowly, so it's wide, is never going to intersect with that very rapidly increasing narrow function that's already starting out above the vertex of the wider function. So here there are no points of intersection, so the answer to number 8 is A. If you have any questions, then please let me know. Otherwise, let's take a look at 9 and 10. Question number 9 asks, for how many positive integers of x does the function h of x, which is equal to, this is a rational function with a numerator of the square root of 3x minus 6, quantity divided by 2x minus 8, have no real values. So for how many positive integers of x does the function that I described before have no real values? And number 10, how many points of intersection are there of the functions g of x is equal to -2 times the quantity x minus 1, quantity squared plus 2, and j of x is equal to 1/4 times the quantity x minus 1, quantity squared minus 3. I'll give you 6 minutes, and after 2 minutes, I'll start to solve. Okay, so for number 9, in the numerator we have the square root of 3x minus 6. So any input value that's going to make that radicand, the number underneath the radical sign, negative, is not going to work, or it's going to produce a non-real value. So if we set that expression less than 0, 3x minus 6 less than 0, when we add 6 to both sides, then we get 3x less than 6. Dividing by 3, remember that inequalities are the same thing or dealt with the same way. They're not the same thing, but they're dealt with the same way as equations, except if you multiply or divide by a negative number, or if you take the inverse of all sides, then you have to switch the direction of the inequality signs around. Here, we didn't do that. We added 6, and then we're dividing by positive 3. So we're not dividing by a negative number, so this is all fine. It's just exactly how you would go about it algebraically if you had an equation. So 6 divided by 3 is positive 2. There's only one positive integer less than positive 2, and that's positive 1. So we have one integer so far from the numerator that would produce a non-real value. In the denominator, we know that any number, any input of x that would produce 0 is going to produce a non-real value because we cannot divide by 0. So if we take 2x minus 8 and set it equal to 0, that will give us a value for the input of x that will make that denominator 0. Adding 8, we get 2x is equal to 8, and dividing by 2, we get x is equal to positive 4. So positive 1 and positive 4 are two positive integers that will have no real values in the function h of x. And so the answer here is going to be C, which is 2. For number 10, if you recall the vertex form y is equal to a times x minus h quantity squared plus k. So remember that the h is the one that's opposite common sense. So when we have a minus 1 as an h, that's a right 1 shift. So the vertex of the first equation, g of x, is going to be right 1 up 2. So you can start there and just plot a point. Now it has an a value of negative 2. That means it's going to be both narrow and facing downward. So it's going to flip around the x-axis. So we're going to be narrow and we're going to be facing downward. So I drew that in on the graph in the blue ink. The second equation has a vertex of positive 1, negative 3, because we're going right 1, down 3 from the origin. So I plotted that point. Now we have a value of 1/4. So that means that this function is going to be relatively wide and it's going to be facing upward. So when that happens, that's going to produce 2 points of intersection. So the answer to number 10 was C. If you have any questions, then please let me know. Otherwise, let's look at 11 and 12, and these will bring us up to the end of class today. So number 11, for how many values of, for how many positive integers of h, that should say x, so I apologize. I'm going to change that. So that needs to be x, the input value. For how many positive integers of x does the function h of x equal, the numerator here is x plus 4, divided by the quantity x squared minus 5x plus 6, have no real values. Number 12 asks, how many points of intersection are there of the functions g of x is equal to 2 times the quantity x plus 2 quantity squared minus 1, and j of x, which is equal to 1/5 times the quantity x plus 2 quantity squared minus 1. I'll give you 6 minutes, and 2 minutes in, I'll start to solve. Okay, so for number 11, there's no square root in the numerator any longer, so there's nothing that's going to invalidate the numerator with respect to the input of x. So the numerator is fine. X plus 4 is a perfectly fine expression. It's not, nothing is violating there. If you plugged in 0, if you plugged in -4, you can have a 0 in a numerator. You just can't have a negative number underneath the radical, and that was the principle we were trying to avoid or investigate in the other problems. So there's nothing we need to do with the numerator, but in the denominator, any input that creates a 0 overall will be a problem because we are not allowed to divide by 0. So factoring x squared minus 5x plus 6, we're going to get x minus 2 times x minus 3. So we have factors of positive 2 and positive 3, so that means that there are 2 positive integers of x that will produce non-real values for the function f of x, h of x, excuse me. So that's answer selection C. And now for 12, how many points of intersection are there between these two functions? So you can see from the vertex form that both of them have the same vertex. We have a horizontal shift left 2, and we have a vertical shift down 1. However, the first equation opens up and is very narrow because it increases fast because it has a leading a value that's greater than 1. The a value in g of x is 2, whereas the a value in j of x is 1/5. That 1/5 is in between 0 and 1. When the a value is in between 0 and 1, that's going to be a wide function. So they both have the same vertex, but then j of x is going to be wide and open out. G of x is going to be narrow and go straight up. So they're only going to have one point of intersection, and that's going to be right at their vertex. So the answer to number 12 was B, or is B. If you have any questions on anything that we've done today, then please let me know in either the comment section, or you can comment me on any of my social media platforms that, or not my social media platforms, but my social media accounts that are listed in the description below. Otherwise, I hope you have a wonderful day. If you find these videos helpful, then please like and subscribe and share with your friends. But otherwise, Dr. Tot, do you want to say goodbye? Come on, let's say goodbye to everybody. It's a very good class. Let's say bye. Can you say bye? Barely. Bye? Can you say bye? No? Okay. Very good. Thank you guys very much for watching. I hope you have a wonderful day, and I'll talk to you all very soon.